Welcome to lecture 41. So, this is week 9 and we will start today flow measurement. So, in this week we will talk about measurement of flow. Measurement of liquid flow or measurement of gas flow is important in many chemical process industries. Is particularly important when you look at operations or manufacturing processes that happen continuously. For continuous operating processes, there will always be flow of raw materials, products, waste, utilities, etc. And it is very important that we be able to measure as accurately as possible the flow of liquid streams or gas streams in several chemical process industries. So, the motivations for flow measurement are as follows. The measurement and control of liquid or gas flow is vital to many process industries such as oil, power, bulk chemicals, water and waste treatment, etc. The manufacturing processes that run as continuous operations involve the movement of raw materials, products, waste through pipes and ducts throughout the process. These fluids can range from thick oils with high density to very light gases. It is important that we know exactly how much fluid is passing through a point at any given point for a safe and economic operation. It is possible that some flow measuring instruments work better with some groups of fluids and less well with others. It is obvious because you will be handling fluids which will vary from say very thick to very light. So, there will always be flow measuring instruments which will work better with some group of fluids and less well with others. In this week, we will learn about various flow measuring instruments and their applications. So, today we will classify various flow measuring instruments and then we will talk about an important principle on which a certain class of flow measuring instruments are designed. This is known as Bernoullis principles. So, we will talk about Bernoullis equation. This is how we classify various flow measuring instruments. Again, this is not the only classification that is available. I have been saying this for all measuring instruments because there are various ways of classifying the instruments into different categories, and what you see on the screen is one possible way of classifying the flow measuring instruments, and we will follow this classification for the purpose of this course. Broadly, I classify the flow measuring instruments into two categories. One is flow of fluids in closed pipes, another the flow of fluids in open channel. Of course, flow of fluids in closed pipes finds many more applications, and under flow of fluids in closed pipes, we have classified various flow measuring instruments under 5 different categories. First, constant area variable pressure drop meters. Under this, we will talk about orifice plate, venturi tube, flow nozzle and pitot tube. Then we have variable area constant pressure drop meter, and we will talk about rotameter. Third, velocity measurement type, we will talk about hot wire anemometer. Then mass flow measurement type, we will talk about Coriolis flow meter. And then positive displacement type, we will talk about Newton disc. Under flow of fluids in open channel, we will talk about wear types flow meter. Let us go through some basic principles. First, average rate of flow. In a flow through pipe, the velocity of a fluid is the rate of flow of fluid particles in the pipe. The speed of particles in a fluid flow varies across the flow. At the walls, the velocity of the liquid particles is practically 0 and the particles will have the maximum velocity at the center. Thus, the average rate of flow is used in flow calculations. The units of flow velocity are say feet per second or feet per minute, meters per seconds, etc. The units of flow rate, if it is volumetric flow rate, we will express it as volume unit per time such as meter cube per second. If it is mass flow rate, we will express in mass unit per time such as gram per second. Next, we will talk about types of fluid flow. In laminar flow, the fluid travels as parallel layers known as streamlines that do not mix as they move in the direction of the flow. If the flow is turbulent, the fluid does not travel in parallel layers, but moves in a haphazard manner with only the average motion of the fluid being parallel to the axis of the pipe. If the flow is transitional, then both types may be present at different points along the pipeline or the flow may switch between the two. In 1883, Osborne Reynolds performed a classic set of experiments to show that the flow characteristic can be predicted using a dimensionless number known as Reynolds number. The Reynolds number, expressed as Re, is the ratio of the inertia forces in the flow to the viscous forces in the flow and can be calculated as dV rho divided by mu. Here d is the diameter of the pipe through which flow takes place, v is the velocity, rho is the density of the fluid and mu is the viscosity. If Reynolds number is less than 2000, the flow will be laminar. If Reynolds number is greater than 4000, the flow will be turbulent, and if the Reynolds number lies in between 2000 and 4000, the flow is transitional. Thus, the Reynolds number is a good guide to the type of flow. So, this schematically shows laminar flow. See how these fluid particles are moving in parallel with each other. This is turbulent flow, where it is all haphazard, and this is transitional. So, you see a mixture of laminar and turbulent in transitional flow. So, these are the velocity profile. Now, we will talk about continuity equation, which plays a very important role in flow measurement. The continuity equation states that if the overall flow rate Q in a system is not changing with time, the flow rate in any part of the system is constant. So, consider a flow through a pipe where the cross sectional area is changing from A1 here to A2 here. The velocity is V1 here, the velocity is V2 here. The pressure is P1 here, the pressure is P2 here. This is point 1, this is point 2. So, the velocity and pressure at point 1 are different from the velocity and pressure at point 2. If the overall flow rate in the system is not changing, between points 1 and 2, this relationship must hold true. That means, the volumetric flow rate Q is the product of cross sectional area and velocity. So, the volumetric flow rate Q is equal to cross sectional area and velocity product here, which is same as the cross sectional area and velocity product here. So, Q is A1 V1 equal to A2 V2. As an example, let us consider if a pipe goes from 9 centimeter diameter to 6 centimeter diameter, and the velocity in the 9 centimeter section is 2 meter per second, what is the average velocity in the 6 centimeter per second? So, here you have 9 centimeter diameter and the velocity is 2 meter per second. Here the diameter is 6 centimeter, you have to find out the velocity. So, this is a straightforward application of Q equal to A1 V1 equal to A2 V2. So, you can find out V2 as A1 by A2 into V1. So, A1 is pi d square divided by 4, A2 is pi d square divided by 4. You can also write pi r1 square divided by pi r2 square into V1. So, A1 can be found out as pi 9 centimeter pi d square by 4. Similarly, A2 can be found out as pi 6 square divided by 4, and V is given as 2 meter per second. Put all these numbers, take care of units, and you will get V2 as 4.5 meter per second. Remember, this is in centimeter, but these are in meter per second. So, you must take care of units. Next, we will start our discussion on constant area variable pressure drop meters. Under this category, we will talk about orifice plate, venturi tube, flow nozzle and pitot tube. To understand the working of constant area variable pressure drop meter, we must talk about Bernoullis equation first. So, first we talk about Bernoullis equation or Bernoullis principle. The Bernoullis equation is an equation for flow based on the law of conservation of energy. This is the starting point for understanding the principles of the variable pressure flow meter. So, Bernoullis equation is basically a statement of conservation of energy. The Bernoullis equation gives the relationship among fluid velocity, fluid absolute pressure and height above some reference line for a fluid flowing through a pipe of varying cross section. So, consider the flow of a liquid through a pipe whose cross section is varying. So, cross section here and cross section here are different. The height of this pipe is measured from this reference line. So, this point is the height from H1 from this reference line and this point is at a height of H2 from this reference line. Bernoullis equation says that between points A1, points 1 and 2, this is point 1 and this is point 2, the sum of pressure energy, kinetic energy and potential energy is constant. At point 1, the pressure energy is P1 by rho g, at point 1 the kinetic energy is V1 square by 2 g and the potential energy can be expressed as potential head H1. So, P1 by rho g plus V1 square by 2 g plus H1 is equal to P2 by rho g plus V2 square by 2 g plus H2. So, sum of pressure energy plus kinetic energy plus potential energy equal to constant. Here P1 is absolute pressure, V1 is the fluid velocity, rho is the density of the fluid, g is acceleration due to gravity and h is height from the reference line. This Bernoullis equation is applicable to incompressible fluids, steady flow along a streamline, no energy loss due to friction and no heat transfer. So, remember sum of pressure energy, kinetic energy and potential energy is equal to constant. Now, consider the flow through a pipe of varying cross section and the pipe is horizontal. I have point 1 here, I have point 2 here. So, since the pipe is horizontal, H1 is equal to H2, the H1 and H2 as we shown in the previous slide. So, they are same. So, then if I apply the Bernoullis equation, that means if I apply this equation, P1 by rho g plus V1 square by 2 g plus H1 equal to P2 by rho g plus V2 square by 2 g plus H2 between 1 and 2 and H1 and H2 are same, what I get is P1 by rho g plus V1 square by 2 g equal to P2 by rho g plus V2 square by 2 g. So, if you rearrange this you will get this P1 by P2 by rho equal to V2 square minus V1 square by 2. If we apply continuity equation between point 1 and point 2, I can write as A1 V1 here and A2 V2 here, they will be same as the volumetric flow rate Q. Now, if I combine these two, I can write Q equal to A2 V2 and an expression of V2 can be obtained from this, and I will be able to write Q equal to A2 V2 equal to A2 by square root of 1 minus A2 by A1 whole square into square root of 2 into P1 minus P2 by rho. Thus, change in flow rate through a restriction can be measured in terms of differential pressure across it, see P1 minus P2. So, what I did is, I am considering a flow through a horizontal pipe of varying cross section. So, H1 equal to H2, apply the Bernoullis equation between point 1 and point 2, I get this. At point 1 and 2, I apply continuity equation, I get this, I combine these two equations and I get this. And note this equation, A1, A2, these are all related to the dimension of the pipe. So, the volumetric flow rate is related to the pressure difference P1 minus P2 across the flow restriction. Note, here is a flow restriction because of change in this dimension. In practice, we add a correction factor CD known as discharge coefficient, which depends on Reynolds number. So, this is the equation we got by combining Bernoullis equation and the continuity equation. So, this is the idealized volumetric flow rate. In practice, we will add a correction factor known as CD, we call discharge coefficient, and QA, Q actual will be this Q multiplied by the discharge coefficient CD. So, this is the expression I get for actual volumetric flow rate through a pipe where we have a flow restriction. P1 minus P2 is the pressure drop across the flow restriction. Velocity of approach factor is this term. So, you look at this. So, velocity approach is 1 by square root of 1 minus A2 by A1 whole square. Similarly, the flow coefficient is this term CD by 1 minus A2 by A1 whole square, square root of that. For laboratory experiments, a Utube manometer may be used to measure the differential pressure head delta H, because we know P1 minus P2 equal to rho G into delta H. So, this is the pipe of varying cross section. So, you have a flow restriction here. So, Utube manometer can be used to determine the differential pressure that happens between point 1 and point 2. So, this P 1 minus P 2 can be replaced as rho g delta H. This row and this row will get cancelled, and what you will get is Q A is this. So, this part will be this part, because P 1 minus P 2 equal to rho g H. However, for industrial practice, use of a Utube manometer may not be convenient, and for industrial practice usually a diaphragm is used for measuring the pressure drop. A diaphragm with one pressure on each side will deform according to the pressure difference. We have talked about diaphragm pressure measuring instrument while discussing pressure measuring instruments. Now, we talk about two important aspects of flow measuring instruments. They are known as rangeability and turn down ratio of flow meters. Rangeability refers to the minimum and maximum measurable flow rates with specified accuracy. For example, if the maximum flow rate is 100 liter per minute and the minimum flow rate is 10 liter per minute, the rangeability is 10 to 100. Turn down ratio conveys the same information as rangeability, but in a slightly different way. Turn down is the ratio of maximum flow to minimum flow. So, basically turn down ratio is maximum flow rate divided by minimum flow rate. For the same flow meter we used in the rangeability example above, that means whose maximum flow is 100 liter per minute and minimum flow rate is 10 liter per minute, the turn down ratio will be 100:10. Remember, these minimum and maximum measurable flow rates, we are talking about the flow rates which matches with the specified accuracy. Let us talk about turn down ratio a bit more. If a given flow meter has a 50:1 turn down ratio, the flow meter is capable of accurately measuring down to 1/50th of the maximum flow. Thus, if the flow meter has a full scale rating of 20 liter per minute, the flow meter will measure down to 0.4 liter per minute of flow, because 1/50th of 20 liter per minute is 0.4 liter per minute. If the calibrated high flow is 25 liter per minute, then the lowest that can be measured is 0.5 liter per minute. Why 0.5 liter per minute? Because it is 1/50th of 25. If the application requires that the calibrated minimum flow is 0.1 liter per minute, then the maximum flow rate that can be measured is 50 times 0.1 liter per minute, that is 5 liter per minute. So, this is how you can interpret the turn down ratio. Now, look at the diagram on the screen. In this figure, this H is equal to 7.5 meter. The area at point 2 is 0.5 meter square and the area at point 3 is 0.3 meter square. G is given as 9.80 meter per second square. We have to find out the pressure at point 2. So, we have to find out what is P2. So, I will give you the sketch of the solution procedure. First, what you will do is, let us try to find out the velocity at point 3. Let us try to find out first at velocity at point 3. So, find out velocity at point 3, what we can do is, you can write the Bernoullis equation between point 1 and point 3 as P1 by rho g plus 0 plus h equal to P3 by rho g plus V3 square by 2g plus 0. Note the reference line. Note that P3 equal to P1 equal to 1 atmosphere. This equation will allow you to calculate V3 and V3 will be able to calculate as 12.12 meter per second. Note that the value of H is 7.5 meter. So, we have got V3. Once I have got V3, I will be able to get V2 by using continuity equation as Q2 equal to A2 V2 equal to A3 V3. A2 A3 is given. So, this will allow you to compute V2 as 7.27 meter per second. So, I have now calculated V2, I have now calculated V3. Now, apply Bernoullis equation between point 2 and 3. If I apply Bernoullis equation between point 2 and 3, I will write P2 by rho g plus V2 square by 2g plus 0 because reference line equal to P3 by rho g plus V3 square by 2g plus 0. So, this is between point 2 and point 3. Between points 2 and 3. So, once you put in all the values, you will be able to calculate P2 because you know P3, there is 1 atmosphere. So, P3 you know is 1 atmosphere. So, that is equal to 101.3 Pascal, sorry, kilopascal. Okay. So, V2, V3 we have found out. So, you will be able to find out P2. So, P2 we can calculate as 148.32 kilopascal, but this will be absolute. So, if I want to find out in gauge, you have to subtract 101 0.3 kilopascal, the atmospheric pressure. So, that will be equal to approximately 47 kilopascal gauge. So, this is how you can solve this problem. So, what you do is, first you basically apply the Bernoullis equation first between 0.1 and 0.3 to calculate V3. Once you get V3, you use continuity equation between 0.2 and 3 and calculate V2. So, at this stage I have P1, P3, V2, V3. Now, between 0.2 and 3 I use Bernoullis equation and then calculate P2. So, I stop today here, and in the next class we will talk about examples of pressure measuring instruments that make use of Bernoullis equation, such as orifice meter, venturi tube, etc.